Okay, so I have been asked to teach, not teach, the wrong word. You are supposed to teach. I am supposed to perhaps motivate you to teach dynamics. Okay, and the reason I was given was that in most college curricula, in fact, in most institutes that I know of, dynamics is not taught, or if it is taught, it is supposed to be taught in किसी को बताना नहीं, पर हम तुमको चुप कर डायरेक्ट पढ़ा के निकल रहे हैं यहाँ से, ठीक है. So my in half an hour I am trying to go to convince you that perhaps this is the best course and the most important course that you can ever teach anybody in any branch of engineering. Okay, if you are a computer scientist sitting in there and thinking क्या बकवास कर रहा है, I am telling you it is the most important course. All right, not programming, okay, not circuit theory, this is it, and let us see if you are convinced at the end of it. Okay, okay. So why? So I will broaden the question and I will ask, why teach mechanics? Okay, dynamics is a subset of the broad field of mechanics. So why teach mechanics? So I will tell you why. So it is the most natural field to bring together the 4 or 5 elements that constitute any scientific or technological inquiry. What are the 4 or 5 elements? Mathematical modeling and techniques. What does that mean? That means that you see something happening, it is too complex, what you do is you make a mathematical model out of it. Okay. So the computer scientists amongst you can imagine that you see people wanting to meet or not wanting to meet, or wanting to chat or not wanting to chat, and you abstract it and make a mathematical model which is called Facebook. Okay. It is basically a program which is executing commands following an algorithm. It is a mathematical model. Okay. How do you solve mathematical model? By techniques. Okay. It is the first instance of our trying to understand natural laws of physics before electricity. This was it. It can often be demonstrated with simple experiments and which intuition and experience. ये तो होना ही था. If you drop an apple, it has to fall down. That is my experience, right? But it can explain intuition experience, it can also defy them. Okay, can also defy them. So that is why it is most important. So this is the first time that you go through these processes together. Okay. So even if you are not going to do mechanical engineering, that is why when I was a student at IIT Kanpur a long time ago, dynamics was compulsory to all branches, not just engineers, not just mechanical engineers, because and there is a story in which some physics people said, we do not need to teach this, we want to study atoms, and anyway this is easy. So they were said, fine, if it is easy, here is a question paper, please solve it. If you can, we will not make it compulsory. They were unable to solve it. This is a true story. That is why until recently dynamics was compulsory for all possible students. So I encourage even those amongst you who are not mechanical engineers to believe me when I say dynamics is the most accessible way to understand the methods of scientific inquiry. Okay. So then again, it is fun to teach and it is fun to see. So why is that? So I will show you 4 videos which will play simultaneously, and you can look at them for about a minute and decide if they are kind of fun or not. Okay. So you see a pendulum, but not just one, many of them, and okay, that is interesting. Okay. Now this video, let us wait for it to stop, and then okay, this one, let us see. So what you see is a disc which is falling. You can see it in a kitchen where a plate falls. Okay. Now many of you will often have seen something called 1 by 0. What is it called? It is also called a singularity. Okay. So it is a singularity. You can't really, when things go bad, they go bad through singularities. This disc, what you are seeing right now, is the approach to a singularity. And if I had a volume control, if I do not know if this has volume or not. Let us see. Yeah, I think you can. So let me see if I can try this again. So I am going to make you hear a singularity. Can you see? Can you hear it? Could you hear it? Let's try again. And that one I don't want. I want this one. Can you hear it? I don't know if you can. So as it falls, if you remain really quiet, maybe you can pick up something. So he spins this egg, which is already spinning wrong way. I wanted to spin from this point. Okay, so it stands up. Okay, so he's going to start spinning this, and it stands up. Why should that surprise you? Okay, it should surprise you if you have done dynamics. It is very interesting is that it is spinning about a long axis. Okay, rocket engineers discovered very soon, and I will show you later, that this axis of spin is unstable, that is stable, but the body chose to go from stable to unstable. Okay, so it makes it interesting because it seems to be defying laws of physics. Similarly, this one, let's see if we can. So he is going to spin this object. Forget this video. So he is going to spin this. It spins very nicely. There is nothing, no problem in this one. Okay. But if you try to spin it the other way, it's not going to spin. In fact, it's going to reverse direction. Okay. And nobody created it. This one is created. I once fell into a river, and when I came out, I had one such stone which behaved like this. So it's actually a very old toy. Okay. So rivers, the stones sometimes behave this in this way. They would spin in one direction but not the other direction. Chal raha hai abhi? Okay, now you hear this sound. Normal sound, nothing very special. It's becoming faster. Okay, what you heard was a mathematical singularity. If you were to actually write down the equations of motion and solve it, you would see something blowing up. So what do you think? What was blowing up? It was spinning very fast. I mean, if you look at it this time, if you look at the lines, they are actually going very slowly. It is not spinning very fast, but the contact point is moving exceedingly fast. How fast? It approached infinity. It's faster than light. I just showed you something moving faster than light. You just learned something, nothing can move faster than light. But I have done a simple tabletop dynamics experiment and made you hear something moving faster at light. I will let you figure out why Einstein is right and this is right. I will leave it for you. Okay. So anyway, so point is, all of these questions, they look very simple. You can buy them in toy shops. You will see them on the tables of bosses, and they all lead. So we can get rid of the sound. They lead to research. So here are 3 papers. You saw this, the thing which spins in one direction but not the other. Paper by Kane from Stanford University. The egg or the ellipsoid which stood up. Paper again by Kane from Stanford. Pendulum, the many pendula which were hitting each other. Paper by Arindam Chatterjee, who will talk to some of us tomorrow. Okay, and they all got the dynamics right, and here is someone who didn't. That's a paper on the Euler disk with wrong dynamics, but published in, I will let you guess, published in Nature, and it's wrong. Okay, I mean, it's demonstratively wrong, but published there, wrong dynamics. So, you can get dynamics right and get published, you can get dynamics wrong and get published, is win-win. Okay. So, here is this, this is in the space station, no gravity. What you see is a pack of cards spinning very nicely and continue to spin, no problem at all. He will try to spin it about some other axis now, that is not so nice. Okay. In fact, you do not see, I mean, he will try it about this one, this will be again be nice. Okay. So, I told you that any body has 3 axes, 2 are stable, 1 is unstable. Okay. So, out of 3 axes, 1 is smallest, 1 is largest, the middle one is always unstable, and this is very important. Well, for me it was important, it got me my first publication. Okay, just this idea. Okay. It is also useful. It is useful because it is used in cars. All these, okay, let us see if this video is running a little slowly. So, what you see are cars doing very complicated motions. This car is doing complicated motion, this car is trying to not slip down, this is trying to climb a hill. This is the test done on automobiles. Cars are very complicated machineries. That is a typical diagram of steering and suspension mechanism. How will I solve it? I will show you towards the end. Many of these questions can be answered by second year undergraduate dynamics courses, they can be. All those papers I showed you were based on second year dynamics, not more. Okay. So, what are our tools? We do kinematics, how do objects relate to objects geometrically. We draw free body diagrams to isolate what are the forces acting on the object. We do dynamics to relate forces to motion. This is where laws of physics come in. It is, you do not see, you can experience a force, you can't see an electric current. Okay. That is why it is accessible. If I tell you that something, the capacitance can store energy, you can't imagine it, but you can imagine a spring storing energy. That is why it is accessible. Okay. So, I showed you this, right. This is a book in the space station flowing, rotating nicely. Okay. That is the longest axis, it is rotating about the longest axis. This is the shortest axis, both are stable. Now, he will try to rotate it about. So, these 2 axes are stable, but the intermediate axis is not stable. Why is that interesting question? I will just show you, let this video finish. That is unstable. Okay? All right. Projectiles, so that is a projectile, that is a tank missile. It is rotating about its shortest axis. The shortest axis in the presence of air is unstable. So, why do you think it is going straight? Why is it not going unstable? Any guesses? The answer is in the video. If you look at the video closely, you will see it is doing something. Take a guess, you can't be wrong. It is also rotating, that is called rifling. Okay. And this lower video, well, we skipped it. So, anyway, the point of these videos was just to show you that all of these things are accessible. You do not need advanced dynamics for it, you do not need university education for it. We can all understand it based on second year dynamics principles. Okay. So, that is what the tank rifle does, it rotates the projectile, it makes it stable about the shortest axis. Okay. Helicopters. So, we in IIT Kanpur we have the international expert on helicopters, and I forgot to get you a picture of the book he wrote, but inside the book I was very happy to see everything is based on second year undergraduate dynamics. Here are some pictures taken from the book where he is modeling helicopter blade as interconnected rigid bodies. drawing free body diagrams like these, free body diagram of the helicopter, okay. Not some 7th year of PhD course, 2nd year undergraduate dynamics. Let me come to something which I know a little bit more about. Dynamics helps explain observations. What observations? See, here is an observation. These dots are something called asteroids. Do you know what asteroids are? So, let me show you a picture of an asteroid. That is an asteroid. That is a real picture, and it is very odd shaped, it rotates. So, there are many such asteroids, and here is the sun, there is Jupiter, and what you find is most of the asteroids are between Mars and Jupiter in this belt, but there are two groups which are here and here. Now, why are they there? Why is nothing here? You understand, you are seeing something and it just puzzles you. What do I need to explain this? You need to do a course in dynamics and then you will know it. Okay. So, let me show you why. So, that is these are equations of dynamics solved to give you something. That is the sun, that is Jupiter. Okay. And dynamics will tell you that there are 5 equilibrium points. 5 equilibrium points mean if you rotate with on this line connecting Jupiter and sun, if you sit on this line, then there are 5 points where an object can be at equilibrium. They are called L1, 2, 3, 4, 5. There are 5 points. You can imagine some point being equilibrium at L1, right? Something is pulling towards Jupiter, something is towards the sun, sun is bigger. So, this point has to be closer to Jupiter, right. Similarly, there could be one point here and one point there, but there are actually points over here and there, L4, L5. It is hard to imagine equilibrium points L4 and L5. What is even harder is if I ask you the question, out of these 5 points, which one is stable, which ones are stable. By stable I mean that if you put something at that point, but make an error and it is slightly elsewhere, it will not remain close. So, out of these 5 equilibrium points, which ones are stable? You are saying L2 is stable, okay. What else? Take a guess, nobody is wrong here. Okay, so L2, L3. Well, the answer is, again as I said, it will defy your intuition. L1, L2, L3 are all unstable. L4 and L5 are stable, and because they are stable, therefore, nature happens to be there. There is no L1, L2, L3 points here. At L1, L2, L3 you will not find any asteroids, but at L4 and L5 you will. Okay. So, what I just said, sometimes it will follow your intuition and sometimes it will not. Okay. Let me, there is another interesting paper, this was also published in Nature, okay, and it also is, it was brought about by some observations. So, what they did was that here is the asteroids, many asteroids, they can identify families of asteroids. So, they say कि भाई जैसे कि आप गुप्ता परिवार के हैं, आप श्रीवास्तव परिवार के हैं, तो मालूम रहता है ना किस परिवार से आ रहे हैं, दादा सब पता रहता है. Similarly, they can group asteroids together. You belong to the same family because you have the same mineral content or something is similar. Okay. So, there is something called a Coronis family. What is interesting about Coronis family is that this is a plot of objects which rotate in retrograde manner and prograde manner. What is the difference? Well, let us see. So, if I am going, if that is the sun and I am moving around the sun, if I rotate like this, it is prograde, but if I rotate opposite to my orbital motion, it is retrograde. Two different times, right? Plus rotation, minus rotation. What they find is that nearly 50% of the objects are retrograde, 50% are prograde. That is automatically interesting. How would that happen? Okay. But you can say, by dekho, 50% chance of getting a girl, 50% chance of getting a boy. So, it is all right. Okay, all right. But more interestingly, these objects are randomly created. So, why are they not tumbling? Why are they rotating nicely about a fixed axis? Okay. So, all of them are rotating, all the retrograde ones are rotating exactly the similarly, and the prograde are rotating exactly similarly. So, you see just two, there is no distribution. So, why is that? And it took them a lot to find the answer. The answer was, if you can read here, thermal torques arising from differential solar heating. That means light pressure can cause dynamics, can influence dynamics of very large bodies. Okay, so let me show you a video which demonstrates this. So, what you have here are rubber bands tied to a disc, and I am going to heat only some of those rubber bands, and let us see what happens. So, this is heating these rubber bands, but not those. So, when you heat something, it will relax, and heating, differential heating can cause rotation, and there it rotates. Okay. This also falls under the simple experiment whose ideas helped to understand why that was happening, help to understand something which you will never see in your lives. They are so small, they are pixels in a telescope. Okay. That is the breadth of dynamics. Okay, so, where am I? Done this, and let me end with saying that dynamics can help explain really complex systems. So, let me just show you this video. You will see some grains and 5 balls fell, and interestingly they did not fall in a line, but they will end up in a line. This is soil. Okay. All together, look, they are adjusting, they are trying to get in a line, but now they have different diameters, large, small, one fell faster, smaller. Oh, how interesting, they are again in a line, right. Different densities, heavy, light, heavy, lighter, lightest, again in a line, right. It can all be explained second year undergraduate dynamics. Here is an experiment from my lab. This is from my lab. Okay. So, I have a mixture of grains. You are looking into the table. So, gravity is into the table. Okay. So, I am just shaking the grains. There are 2 grains, white is large, green is small. Chana or moong? Chane ke chana nahi, matar. Oh, they are separating. They are separating even more. In fact, they separate completely. Number of grains is about 10,000. Okay. How does it work? Okay. How will you find the answer? Okay. So, that is, I showed you an example where I separate 2 grains, white and green. I have got 3 grains now, sarson, moong, matar, mixture, separation to all 3. So, I can separate 3 grains. Experiment to kar liya. How will, suppose I am an entrepreneur and I want to sell it to somebody, I have to explain, I know how it works, right. So, I can improve it, make a better machine, things like that. So, what you do is you can't write down by hand equations anymore, you have to create a computer program, and computer scientists should get interested in this. You have to solve equations of dynamics for thousands and thousands, millions and millions of particles, that is millions of. So, for each particle you need 6 equations. If I have 1,000,000 particles, if I have 1,00,000 particles, you need 6,00,000 equations. How fast a computer can you build to solve 6,00,000 equations simultaneously while I still remain alive? Okay. So, you can't do it on one computer, you need to have 7-8 computers, but they must work in parallel. I need parallel programming. So, that code my student created using parallel programming. but using second year undergraduate dynamics. Okay. I am not joking, just that, not nothing more than that, and that is a simulation. And how good is the simulation? Experiments, simulations. Why did I do a simulation? Once I have a simulation, I can look inside and figure out why things are happening, which I did. How complex was the problem? It took me 5 years to solve it. But the foundation, I will repeat again, was second year undergraduate dynamics, but coupled this time with computer science, a lot of computer science. Okay. So, thank you. Let me say that change is inevitable. We all understand that, right? And what is dynamics? It is about the rates of change. So, dynamics is inevitable. Okay. Okay. Thank you. So, I think I am out of time, but if you have one or two questions, I will be